Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Go ahead and raise your hand if you did not get a red mark for today. Okay, then let's go ahead and get started. So we can interpret a linear relationship in context, complete with units, right? Using the same quantities we've dealt with, right, with linear equations all unit long. It's just that now the variables in that linear equation are connected to real life quantities. They have meaning, right? They have meaning in context. And so let's go ahead and determine things like the rate at which Sarah reads with units. Let's go ahead and write a linear model that gives the remaining pages p as a function of the night's n. Let's interpret the y-intercept in our model, and when does our model predict that Sarah will finish her book? And so we can answer each of these things. Let's suppose Sarah's been reading her book for the past week. After reading for one night, she had 914 pages remaining. At the end of the week, she had only 512 pages remaining. Sarah thinks that she reads at a roughly constant rate. So let's determine the rate at which Sarah reads with units. So we want to first go ahead and define our variables. It looks like further on, we're told we want a linear model with p pages and as a function of n nights. So we'll go ahead and let n equal the number of nights that she's read. So n is the number of nights that she's read. P will be the number of pages remaining in her book, and then we can get two-ordered pairs. We can then use those two-ordered pairs to determine the slope or rate of change in the number of pages remaining with respect to the number of nights and she's read. So we'll let n equal the number of nights she's read. We'll let p equal the number of pages remaining. And now we've got two ordered pairs. After one night, she's got 914 pages remaining. Go ahead and tell the class another point I have on this linear relationship. What's another point I have? Ben?
At 7 nights, she's at 512.
Awesome, thank you. Raise your hand if you have the same two ordered pairs on your own. So you already had those ordered pairs? Great. So after a week, that would be 7 nights. Good. Thank you. Now we'll calculate my slope m, right? My slope m using our age-old middle school formula, y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. Go gadget arm. We'll go ahead and do that. So how do we do there? That's 100, 200, 300, 400, less 12. So how do we get? Is that 398? 402? Negative 402? Is that right? All over? I got this one. 6. We'll go ahead and reduce that. When you reduce that, what did you get? Logan?
Negative 67.
Negative 67? Raise your hand if you had the same thing as Logan. Negative 67? Negative 67? Awesome. Now let's go ahead and interpret this slope number in context. And so, determine the rate at which Sarah reads with units. That's negative 67. My top number came for pages. My bottom number came from nights spent reading, so it looks like pages per night. So we could say that the pages remaining, right, the pages remaining in her book is decreasing because it was a negative slope number at a rate of 67 pages per night spent reading. Awesome. Next, let's go ahead and write a linear model that gives the remaining pages p as a function of the night n. So we'll go ahead and we can use point slope form to generate an equation, just like you'll have to on your quiz. Remember, y minus y sub 1 equals m times quantity x minus x sub 1, where m is the same slope we just calculated. Logan told us that was negative 67. Y is going to be our pages p remaining, and x will be my independent variable, the number of nights spent reading. But first I'll plug in my point. It looks like y minus either one I could do. I could do the 914 or I could do the 512. I'll go ahead and do the 914. So 1 comma 914. So y minus 914 is equal to negative 67 times quantity x minus 1. Then I'll go ahead and solve for y. Distributing my negative 67 through the parentheses yields negative 67x plus 67. And lastly, solving for y, I get y equals negative 67x plus 67 plus 912. Looks like a whopping 70, 84 less 381, 981. Awesome. And lastly, we'll go ahead and call y, my dependent variable, p, the number of pages remaining, equals negative 67 times n, the number of nights n spent reading, plus 981. Now we're all ready to interpret the y-intercept in context, right? So we'll go ahead and interpret the y-intercept in the context. It looks like my y-intercept was 981. We can see that when 0 nights n are spent reading, the number of pages p is 981. So what does that mean? Well, in the context of my problem, right, if 0 nights are spent reading, there's 981 pages remaining. That must be the number of pages in the book, right, before you start reading. So for our model, p equals negative 67n plus 981. Our y-intercept then, when n is 0, gives me 0 comma 981. And we can interpret that by saying 981 pages remaining when 0 nights are spent reading. What questions do you have about our y-intercept interpretation? Above all, our y-intercept is the value of the y quantity when the x quantity is 0. In this case, the number of pages in the book when 0 nights are spent reading. And lastly, when does your model predict Sarah will finish the book? Again, we'll start with my model p equals negative 67n plus 981. When Sarah finishes her book, what variable, right, p or n, equals what value? So when she's finished her book, what's true about the value of p or n? Eric? If she's finished her book, what do we know about the value of p or n?
P is 0.
P is 0, I'm down. So let's set p equal to 0 and solve for n to determine the number of nights that she spent reading. Thank you. So I'll subtract over the 981. We'll divide both sides by the negative 67. And we'll go ahead and get a decimal approximation. So when you did 981 divided by 67, what does your calculator give you, Ben?
14.6.
14.6. So if we get 14.6, is that exact or dot dot dot?
I think it goes.
All right, so let's do this. If n is about 14.6, how many nights will she have to spend reading? 14 or 15? I would say she'd have to spend 15 nights because after 14 nights of reading, she's still not done. She still have pages remaining. She needs to read 2/3 of the next night. So I would say after 15 nights of reading, she'll be done. Awesome. What questions do you guys have about your Bellwork today? Great. So let's go ahead and take care of our homework. At this time, please make sure your name is on your regression worksheet. That's your scatter plots worksheet. We did 1 together, so everybody's going to get a 1 out of 4 as long as you didn't lose it. Hello, thank you. If you completed numbers 2, 3, and 4, then you'll get 4 out of 4. So at this time, let's go ahead and give yourself credit for those that you completed out of 4. divide, enter, multiply by 4. The number you did is going to be your Infinite Campus score for completion, but then you have your reading questions. If you showed me your 1.8 and 3.7, you're eligible for a 5th point, bring your total Infinite Campus score on to the nearest half point, 0 to 5. So once again, 2 reading questions. If you just did 1 reading question plus a half, you did both reading questions, then plus 1. What questions you guys have on your Infinite Campus score? Okay, let's go ahead and check them. So our first one we did together, the second one paired fat, grams, and calories in selected fast food meals. And so it's okay if you make the graph on your calculator, right, using the stat plot feature, because we were into using the calculators for these problems. So it's okay if you do that on the calculator. However, your regression line, right, rounded to 2 places should be y equals 13.61x plus 150.87. I interpreted the slope by saying for every 1 gram increase in fat grams, the number of calories increases by 13.61 calories. That is, the number of calories in the fast food meal is increasing at a rate of 13.61 calories for every 1 gram of fat in the meal. Either way is fine. My estimation gave 341.37 calories. Raise your hand if you got that estimation. So anybody else get that estimation? So plugging into your regression equation, nice job. Number 3, paired average July temperature with average annual precipitation. On calculator, you can make the stat plot. My equation was y equals 1.65x minus 80.32, and that made a prediction for 43.46 annual inches of rain if the July temperature average was 75 degrees Fahrenheit for the high. And lastly, number 4, paired the year with the number of households, and we let x equal the number of years since 1975. So 1975 would be year 0. That would be 0 years since 1975. 1980 would be 5 years since 1975. 10, 15, 20. My key points then would produce the regression equation y equals 1.36x minus 72.6. For every 1 year increase in the year, the number of U.S. households increases by 1.36 million households. You could also say the number of households in the U.S. is increasing at a rate of 136 million households per 1 year. What questions do you guys have about your regression worksheet? Make sure that your name is on the front side of your Infinite Campus scores box. So you're taking into account your reading questions or not, and pass from the back to the front. We'll get going with our first discussion with sequences, and then we'll have our quiz second half. You should have plenty of time to do your best, but thanks for your help grading your assignment and organizing it. I appreciate that. Thank you, guys. Thank you. All kinds of space the same way. Thank you. Everybody good with your regression worksheet? Thank you, ladies and gentlemen. I appreciate your help. Today, during the first half, we're going to interpret and graph sequences. So we'll take our first foray into the realm of sequences, really setting up for next class period when we do more with them, when we use sequences to model real-world situations. So today is kind of a foundational day. It's not a very long lesson, so you should have plenty of time to do your very best on your linear equations quiz. We'll be doing that the second half. But to ensure that, let's go ahead and get started. So on your note sheet, I'd like everybody to find our sequence definition. A sequence is an ordered list of numbers or objects. Right? So this list of numbers, 3, 9, 27, 81, ... that's a sequence because it's a list of numbers. A specific item in the list is called a term of the sequence. The third term of this sequence would be 27. That's it. let's describe how each term after the first is related to the term before. So what I want you to do is go ahead with your partner right now. Let's see how each of those terms is related, right, from the first one. What could you do to get from one term to the next term? Be ready to share with the class when I call on you. So how are those terms related? Okay, Katie and Braden, what did you guys say? Multiply by 3. Raise your hand if you said multiply by 3. So after the first time we can gain successive terms by multiplying by 3. Absolutely. So our informal rule to get from one term to the next would be to multiply by 3. Now let's give an explicit formula for C. As you know from your reading question, right, an explicit formula is simply a rule, like a function rule, that would tell you, right, what the term value is based on the term number. In other words, I should be able to, given my explicit formula, plug in 3 for the term number, and it give you what you told me term 3 was, 27. So let's come up with an explicit formula for C sub n, this sequence of numbers. Well, I know that if I multiply by 3 from the first term, then I would get the next term. The relationship between successive terms is to multiply by 3. So I bet my formula is going to have a multiple of 3 in it. And what could I do to that 3 in order so that I got the first term? The first term gave me 3. The second term, when I plug in 2 to my formula, will give me 9. The third term, that is when I plug in n equals 3 to my third term, will give me 27. Right? Raise your hand if you've got it. I'm going to use my formula to make this work. What should I do with n, my term number? Adam? Square it. So if I put a 2 here, right, a 2 here, then C sub n would give me 3 squared is 9. That would give me one term, right? That would give me one term. But is it the same every time for a general n? No. It would work for 2, right? So what would I need to do with my exponent? Braden?
3 to the power of n.
3 to the power of n, and then when n is 2, the second term, it would give me 3 squared is 9. When n is 3, it would give me 3 cubed is 27. When n is 4, it would give me 3 to the 4th is 81. Absolutely. So yes, we need an exponent there. We need to put our n up in the exponent. Today we're doing that simply through inspection and guess and check. Next class we'll go ahead and develop rules for determining explicit formulas. But for now we'll do a quick check and we'll try when n equals 3, my third term. Let's see if it gives us 27. Here we go. If I plugged in 3 into n, I get 3 to the third, and what does 3 to the third equal? 3 times 3 is 9 times 3 is 27, so it checks out. My explicit formula works. We're feeling good. Now let's go ahead and consider a different kind of sequence. Let's suppose we have a different sequence called a sub n. And a sub n takes term numbers n and pairs them with output term values in accordance with the function rule 1 plus 3n. So if I plug in the first term number 1, if n equals 1, then I can evaluate my function rule to determine what a sub 1 is. Let's try it. This is just like evaluating a function from unit 1. 3 times 1 is 3 plus 1 is 4. So when I plug in 1 to see what the value of the first term is, I get 4. When I plug in 2 to see what the value of the second term is, I get 3 times 2 is 6 plus 1 is, I get 7. When I plug in 3 to get the third term into my formula, I get 3 times 3, and I get 10. Go ahead and complete it for 4 and 5. Be ready to share. So when n is 4, what do you get? Carson, you?
13.
13, thank you. And when n is 5, what do you get? Marina?
16.
16. Raise your hand if you have the same table. Great. Now let's go ahead and write these as ordered pairs to reinforce the idea that a sequence is in fact a function. A sequence is a function that pairs inputs that are term numbers with outputs that are terms, or terms values. And so these are all, right? These are all ordered pairs that are a member of this relation. A sequence is a function. So 1, 4, 2, 7, 3, 10, 4, 13, 5, 16, if we were following good math manners, we would go ahead and let the reader know that there's a set of ordered pairs and separate those by commas to show the list. Now let's consider the sequence shown in the table. This sequence is from a famous sequence of numbers called the triangular numbers. The triangular numbers take inputs and pair them with the outputs such that 1 is paired with 1, 2 is paired with 3, 3 is paired with 6, 4 is paired with 10, and so on. In fact, the triangular get their numbers from arranging objects or dots in triangular arrays. In the first row, there's 1 dot. In the first 2 rows, there's a total of 3 dots. And the next triangular array would look like this. When my triangular array is 3 rows long, how many total dots are there? 6. You guessed it. If there were four rows in my triangular array, I'd have how many dots total? 3, 6. I'd have 10. And so this is where the triangular numbers come from. The domain of this sequence, because it's a table, is simply a list of inputs, just like we did before. Because it's a table, technically, we would only list those shown. 1, 2, 3, 4, 5. Those are the term numbers. If we thought of this as a function, t of 1, right? T of 1 would be the output produced when my input is 1. That is 1. T of 2 is 3. Go ahead and tell the class t of 5. What would t of 5 be? Will? 15. Absolutely. Thank you. So a sequence is a function. There's different notation with my input versus my function notation, and that's often called a subscript. So let's take a look. Instead of using t of n, a common notation is to use a subscript for the input. A subscript is a label that's set lower and smaller than the regular text, right? Subscript, like in your Microsoft Word 2013 when you're typing, subscript sits a little bit below. It is sometimes called an index because it indicates the position in the sequence. So t sub 4, right? T sub 4 would be the fourth term. What's the fourth term? 10. No big deal. MBD. Easy cheesy. Before we can make a graph, we want to introduce the idea discrete, all right? Discrete function versus continuous function. You guys ran into this in your practice. 3-1 to 3-3 when you guys were dealing with the bananas and apples problem. The bananas and apple problem when you go to the grocery store was a discrete relationship because it doesn't make sense for all continuous values of apples and bananas. We don't get 6.238 bananas when we go to the store. We get 6 bananas, or we get 7 bananas, or we get some other whole number banana number, right? So we call that a discrete function because its graph would be a series of disconnected points, versus a continuous function would be an infinite number of connected points, right? When we connect those points and put arrows on it, now we're talking about a continuous function. Sequences are examples of discrete functions because they're isolated, non-connected points when we make the graph. Not all discrete functions are sequences, but all sequences graphs are discrete functions. Let's go ahead and take a look. As we plot term number, comma, term value, we can create a graph of a sequence. So everybody, let's take a look at our explicit formula. L of n gives a sequence named L based on term number, and I could get L of 1 by plugging in 1 to my explicit formula. When n is 1 for the first term, I get 9 minus 0.5 times 1 is 9 minus 0.5, which is 8.5. L of 2, the second term, is given by 9 minus 2 times 0.5 is 1. I get 8. L sub 3 is the third term. I evaluate my explicit formula when n equals 3 and get 9 minus 1.5. That would be 7.5. And so on. So I can go ahead and create my points by doing term number, comma, term value, term number, comma, term value, and I'll complete the remaining ones. So I get 7, 6.5, and 6. everybody, let's go ahead and plot my L of n. I'm going to plot that in blue to show my sequence. It'll be a discrete function that is disconnected points. And so we're not going to connect them. When we make the graph of a sequence, we simply plot the points on the xy coordinate plane. Ready? Term number 1, comma term output 8.5. Term number 2, comma output 8. Term number 3, 7.5. Term number 4, 7. Term number 5, 6.5. Term number 6, 6. Does everybody see we've got a series of disconnected points? Disconnected points when we graph a sequence. Easy cheesy. Let's contrast that with L of n, the continuous function, that it contains an infinite number of connected points, right? In order to get the difference between L sub n versus L of n, guess what? We connect those. I'm going to throw some arrows on that bad boy too, because it specified the domain is all real numbers. So let's go ahead and grab my line tool, and let's do domain all real numbers, domain all real numbers. Okay, let's compare and contrast the graphs. A sequence is a discrete function. Its graph consists of isolated, disconnected points. A continuous function connects an infinite number of points. Both of them adhere to the same linear relationship. However, the continuous function contains an infinite number of points that are connected. The sequence contains an infinite number of points that are disconnected. And that's how I remember that it's a discrete function, because its graph is disconnected. I continue plotting points, all right, for the blue sequence. I could continue plotting points forever. There's still an infinite number. It's just they're not connected. And that's the difference. What questions do you guys have about our graphs of discrete functions and sequences versus continuous functions? Then let's go ahead and sum it up for our closer. True or false, a sequence is a function. Don't say it out loud, just think. Unless otherwise specified, what is the domain for all sequences? That one we didn't talk about much. So we want to make sure we get a good response written down for our closure. Okay, so we'll go ahead and do a hand raise. We're going to do a sequence is a function. Raise your hand if you think that's a true statement. So we think it's true. And then thanks, hands down. A sequence is a function. Raise your hand if you think it's false. If you think it's false, okay. So let's go ahead and hear why you said you thought that was true. So why do you think it is a function? All right, Katie? It does have a domain and range, but right, so do relations. My domain is the collection of all the first members of my ordered pairings, when the range is the collection of all the second members of my ordered pairings. What is it that makes this a function? Right? Well, I have inputs, right? Inputs that are paired with outputs, such that every time I plug in a particular term number, it's going to be paired with one and only one output, the term value. Every time I plug in 2, I get 8. Right? Every time I plug in 2, I get 8. So this is a function. It's a relation. It is a function. So this is a true. What have you, green for that? What have you, green? I want PDFable, column, baby. PDFable. And lastly, unless otherwise specified, what is the domain? The domain is going to be the collection of all counting numbers. So the natural numbers 1, 2, 3, 4, 5. We'll call that the counting numbers. The term numbers, starting with 1 unless otherwise specified. So the counting numbers include, ready? 1.
Positive integers?
Yes. Yep. 1, 2, 3, 4, forever. Okay? So there are an infinite number of members in most sequences, and their domain is the natural numbers or the counting numbers. You guys are awesome, and look, we're 1 minute ahead of schedule. So we're going to go ahead and take your quiz, but first we need to arrange the desk. So please listen carefully. I'm going to put a starter desk on the line here, carry on the line. So, Olivia, if you kindly slide forward, you're going to slide in front of Eric until your left side is on this line right here. Okay? Then you're going to make one straight, long, skinny line all the way back one desk at a time. So, Taylor, you'll have to scooch back until almost the poster. Thank you. Casey, you're going to go ahead and slide up, and we're going to do 1, 2, 3, 4. You're going to put your front left all the way back. Dakota, you're going to go back to the poster. Perfect. Perfect. Luke, I'll go ahead and stop the recording.